Now let's consider a three-dimensional shape that actually has three variables. In order to figure out what this looks like, what we're going to do is consider all the cross sections. Now, what a cross section is we replace any one of the variables with a constant, and then we look at every slice parallel to that plane. A cross section is not replacing the variable with a specific number. That's something else, and especially replacing a variable with 0, that might actually produce an impossible graph. So I want to consider the xy, xz, and yz cross sections. So the xy means I replace z with a constant. So this would be the equation 2x squared plus 3y squared equals 6 plus k. This one would be 2x squared minus z equals 6 minus 3k squared. And then the last one would be 3y squared minus z equals 6 minus 2k squared. So if I'm looking at the two-dimensional cross sections, then this graph here only has two variables, and that's clearly an ellipse. I'll squeeze that in here. One squared variable, this is a parabola. Again, one squared variable, this is a parabola. This is what the graph actually looks like with the vertex below the xy plane. But what is it called? Well, two of the cross sections are parabola. So I say parabola wins. It gets the title of oid, meaning this is called a paraboloid. But what type of paraboloid? Because that cross section is an ellipse, it's an elliptical. Okay, that's our first example. Now let's consider this graph right here. Once again, we replace one of the variables with constant. So I will have 2x squared plus 2y squared equals 8 plus 4k squared. Because that's a sum of squares with the same coefficients, and that's a positive quantity, we know that cross section is a circle. In the xz, we're going to get 2x squared minus 4z squared equals 8 minus 2y squared. Because that's a difference of squares, it doesn't matter whether this quantity is positive or negative. This is going to be a hyperbola. And finally, in the yz plane, I have 2y squared minus 4z squared equals 8 minus, actually, sorry, this should be k. 8 minus 2k squared. And again, that's a hyperbola. So like before, hyperbola wins, so this is a hyperboloid. Because that's a circle, this would be a circular hyperboloid. We give this one a special name. Hyperboloids are special because this is just one continuous piece, we say, of one sheet. So rather than try to memorize formulas and what they would look like, figuring out the cross sections is actually pretty low level and relatively simple. So let's look at a similar problem now. Now I've made one subtle change. I'm going to change that to a minus. So we would expect that most of our cross sections will be very similar. So in the xy plane, again I get 2x squared minus 2y squared equals 8 plus 4k squared. But this time, that's a hyperbola. In the xz plane, 2x squared minus 4z squared equals 8 plus 2k squared. That's also a hyperbola. Now the yz plane is interesting. So if I throw that over there, I'm going to have negative 2y squared, negative 4z squared equals 8 minus 2k squared. That is most definitely not a circle because these are both negative, and I can't have a negative sum of squares. So let's multiply both sides by negative 1. That changes everything. This is an ellipse, but that part there still has to be non-negative, which means if k is too small, this would be impossible. So for this to be true, k squared would have to be at least 4. So the absolute value of k must be at least 2. Now, since k represented the x variable in this case, there's a gap on the x-axis. So the graph ends up having 2 pieces in this case, and so this is called, in this case, an elliptical hyperboloid of 2 sheets, because there are 2 separate pieces to the graph. Probably the most interesting and yet confounding of all of the shapes that we're going to deal with that involve conics is the next one. So we begin simply enough in the xy plane once again. 2x squared minus 3y squared equals 1 minus k. That clearly is a hyperbola. In the xz plane, 2x squared plus z equals 1 plus 3k squared. That's a parabola. And in the yz plane, negative 3y squared plus z equals 1 minus 2k squared. That's again a parabola. So it's a paraboloid, this time a hyperbolic paraboloid. Now, what makes this one particularly interesting, I've given you sort of a rough sketch. This is what we call the saddle. Imagine an infinite saddle. From one point of view, I'm looking through here. This looks like the peak of the saddle as these cross sections do this. But when I stare straight on, that same point also looks like the low point of the saddle. So depending on your point of view, you might see the high point, you might see the low point. So in actuality, it's neither, and we give this a really clever name. We call this a saddle point. And like I said, probably the most interesting of the shapes. Now, none of these shapes you ever will have to draw. You have to be able to know what they look like, and the simplest way is by just going over the cross sections as I've shown you. Again, choosing one variable at a time to represent a constant, and then describing what the shape is. Now, they don't have to be conic sections. We tend to use conic sections because we can understand them and we can picture them better than anything else. So this completes our entire review of surfaces.